Hello, finance students. This is Dr. John Robinson, and this week we're going to be discussing the time value of money. So, what do we mean when we say the time value of money? Well, let's take as a thought experiment an opportunity to choose between two gifts. So, one is a $10 gift received today, and the other option is a $10 gift received in 1 year. I think for most of us, we would say, well, this is an easy decision. I'm going to choose $10 now, but it's important to understand why that would be. So fundamentally, we as humans have a preference for things sooner rather than later. Maybe there's a feeling they're more likely to materialize, or maybe we have a dislike of waiting, or we can have a nice long list of reasons why, but this is something just that's part of human nature, that we have a preference to have things sooner rather than later. And so a choice between 10 now and 10 later is not a very interesting choice. A more interesting choice would be to offer two gifts, one of which is 9 now, and the other is 10 later, a year later. If you only are allowed to choose one, naturally you expect that some people would choose the later gift now that it carries with it a bonus $1 relative to the $9 gift. Whereas other people might choose the 9 over the 10, being more interested than the former group in receiving money sooner. And then we can imagine a different situation where one person has 9 now and another person has 10 later, and the 10 later person can think, gee, I really would like to trade my $10 later for $9 now, and the $9 now person thinking, gee, I would really like to trade my $9 now for $10 later. And so we have then two people that value each other's goods or wealth more than the other, and it would be natural for them to trade, right? If the $9 individual gave his 9 to the 10, and the 10 gave his 10 to the 9, they both are happier. What this would do, though, this transaction would actually establish an interest rate, because we have a mapping from $9 to $10 a year later, and it sets the price for moving money through time. Right? If there's enough people, some with money now and some with money later, all trading with each other, we can establish a nice percentage rate for traveling through time with our money. And so that's the fundamental thinking behind the time value of money, that people prefer money now rather than later, and therefore there's a price to be paid to move money now rather than later, and there's a price to be gained, a value to be received if we are willing to be patient and receive our money later. Naturally, that means when we talk about time value of money, we're going to be tied up pretty carefully with interest rates. So it was the interest rate that defined the mapping from money now to money later, and so we will spend some time thinking about interest rates and making sure we understand them. Chances are you may think you do, but and further chances you probably don't, at least not as well as you think. So we'll get into some detail about that, and then talk about applying interest rates in valuing a checking account. So by the end of this week, we should be able to accurately value a checking account, including time deposits that arrive later or sooner. So, taking as an example of an interest rate problem, let's imagine I have a 1-month $100 loan, and there's no interest on this loan if you borrow $100 and then later you pay the $100 back. But at the time of payment, so when you pay the $100 back, there is a $3 fee to cover the transaction. So you borrow $100 and then later you pay $100 back plus a $3 fee. So we can ask a question. what is the interest rate in this situation? So one answer to this is that this is not an interest rate, it's a fee, and fee is not the same thing as an interest rate. Okay, so on some level this is true. There's some legal context in which it might matter that we're paying a fee and not interest in this case. But looking strictly at cash flows, there's no difference to our wallet between receiving 100 and then paying 103, and receiving 100 and then paying 100 and then paying 3 at the same time. These are, in cash terms, equivalent. And so we can infer an interest rate from the cash flows of this transaction, even if it isn't necessarily described as interest in the advertising. So if we can ascribe an interest rate to this situation, a reasonable question would be to ask, well, what is the interest rate in this situation? Typically, when I ask this question in a face-to-face class, we can see pretty quick what I'm getting at. Obviously, 3% is a nice clean answer, right? We have 100 in, 103 out. So there's clearly something 3% going on. But usually people will say right away, well, yes, but this is over a 1 month period. And so if we wanted to know what the annual interest rate is, we should multiply by 12 and get 36%. At that point, I usually say, well, what do you think about 42% as an interest rate? And obviously, this is not something that people would think is true, but of course, if your professor asks you, what do you think about 42% as an interest rate, you have to be suspicious that 42 actually is an answer to this question, and this turns out to be true. So why? So what's going on here? So 3% is an interest rate and a valid answer to this question. The key is the units on that 3% rate. So 3% is a 1 month rate compounded every month, right? It's been 1 month, we have 3% interest, and so the 1 month calculated every month is 3%. And that's an accurate statement of the interest rate of the situation. Another way to accurately say this is to say, well, over the course of a year, we will pay 36% interest, but it's actually calculated 3% 12 times. Okay, so the statement, but it's actually calculated as 3% 12 times, means that 36% is an annual rate compounded monthly. So even though we have a 36% interest rate, it really is like doing a 3% interest rate 12 times. And so that's something a little different than just 3%. So in fact, with the 36%, you'd be tempted to say that after a year you would owe $136, but this is not true. Right? After 1 month, you owe 103, and after 2 months, you owe 106 and some change, because that $3 interest that you are accrued in the first month will have now interest on the interest and accrue some extra payments in period 2. So you can see where this is going. The fact that we're having interest on interest on interest up to 12 times, that's going to lead to a higher balance in the loan account at the end of a year if we roll it over. Okay, so naturally we can think about what happens if we change this to 75 cents every week. This feels exactly the same because it's the same amount of cash, but as we can see from our previous discussion, 3% 12 times is different than 36% once, and 75% 52 times is different than 3% 12 times. In fact, if we wanted to find out how much we would owe after 1 year, we would need to calculate the interest on 1 month of borrowing and then repeat that process 12 times. So if you see here on the slides, what we would do is we could say that $100 we would pay $100 plus $100 times the interest rate, and that's what we would owe at the end of 1 month. Clearly, you can factor out a 100 from 100 plus 100 times r, and so we get 100 times the quantity 1 plus r. So I have a note there on the slide that we'll see this a lot. This is absolutely true. 1 plus r is a quantity that is the principal plus interest. So if you can imagine how many times we want to know principal plus interest in a finance class, the answer is a lot. Okay, so 100 times principal plus interest is what you get after 1 month in this case, because the interest rate is a 1-month interest rate. So now on the slide, I ask, well, what about 2 years? Well, naturally, we should have principal plus interest, and that's what I have there in that algebraic expression. 100 is the principal, $100 is the interest, and $100 is the interest. But now we need interest on the interest, so that's 100r is the interest, but we pay interest on that. So it's r times the quantity 100r, or 100r squared. So if it's been a little while since you had college or high school algebra, you may not have picked this up, but if you've had math in your recent educational career, you probably would have noticed right away that we can rewrite this as 100 plus 200r plus 100r squared, and that is a perfect square binomial. So we can factor the first algebraic expression under what about 2 years into the second, where we factor out the 100s, group the 1 plus r's, because now we have 1 plus 2r plus r squared. And that's equivalent to 1 plus r squared. And naturally, you can wonder, well, what if we do another month? Is it going to be 100 times the quantity 1 plus r cubed? And the answer is yes. So for any number of periods, you get that kind of result where you take the cash in, multiply by principal plus interest a number of times equal to the number of periods, and you'll get the resulting amount of money. What's important here is that when we looked at this formula here, or we have 100 times 1 plus r, we never said anything about r at all. It was just a number, and we used it, and that was it. And so, the void that's missing here is we made an additional assumption when we put 3% in for r. If we were to do this problem, the fact that r is 3% already implies that the interest rate for 1 month is 3%. And so we're doing our time period is implicitly 1 month because that's the kind of rate we used. If we wanted to do a different rate, say the annual rate, we would need to change the interest rate to reflect the time period we're interested in. Okay? Which means that interest rates need to have time units, but it's actually more complicated than that. If you go back and think about that 36% rate, that 36% is simultaneously an annual rate and a monthly rate, right? It's 36% over a year, but we're calculating it as 3% 12 times. So that means interest rates, in the way that we generally use them, have double units. You need to know the time frame and the compounding frequency for every rate you use. So let's do another thought experiment. Suppose you give me $100 and I give you $120 back in 3 years. What is the rate in that case? Right? So one great answer to this question is 20%. And if we answer 20%, the units on that 20% are 20% every 3 years compounded every 3 years, because we compound it once. So we can say that we can take that 120, and we know that 100 turns into 120, but we can think, well, what interest rate would take us from 100 to 120? if we apply it 3 times, right? Because there's 3 years, we're interested in an annual interest rate, and then you apply that annual rate 3 times and you get the new number. We can solve for this. We say 100 times principal plus interest cubed equals 120, and then solve for r. So you divide by both sides by 100, you get r as the cube root of 1.2, and you get 6.266%. Right, so a little bit more than a third of 18%. So why is this not just 1/3 of 20%? Well, because of interest on interest on interest, the interest rate actually has to be lower in order to end up in the same place. And so the interest on interest helps you get there, and therefore you can start at a lower rate. So in this case, though, the 6.266%, that is assuming we have an interest rate every year. But what if we wanted to calculate the interest rate every second instead of every year? How would this change the problem? Very little. So what you would get is, instead of 1 plus r, which is the principal plus interest, you get e to the r. And that is for continuous compounding. So that would be if we calculated the interest rate every second and did it over and over and over again over the life of the loan. Naturally, you're going to end up owing a little more if you borrow at a continuous rate than if you borrow at a one-time calculated rate. Therefore, to get to a certain number, you need a lower interest rate for a continuous rate. And continuous rates are handy in terms of algebra because they enable solving for r relatively easily, right? If I have e to the r, I just take the log of the e to the r, and you're left with just r. And so we can solve for the continuous return in a relatively easy manner. So let's take a look at an example of how we might think about converting rate from 1 units to a different set of units. So if I have a 5% rate as an annual rate compounded annually, and I want to convert it to an annual rate compounded monthly. So let's think about that. So if I have an annual rate, and that's how I'll usually say it, as the time frame first and compounding frequency second. So if I have an annual rate of 5%, to get a monthly rate, I would need to know which rate that I apply 12 times will get me to the same place financially as taking this rate annually once. Right? If I have an annual time frame and an annual compounding frequency, I'm calculating it once. And so whatever principal we put in, it would turn into, so principal on the left-hand side would be equal to principal on the right-hand side times 1.05. But then we want to find whatever that would be in 1 month. And so if you solve for a rate in that context, it ends up being a 12th root of 1.05 because we need the monthly rate rather than the annual rate. And then if we subtract 1, that would get us our monthly rate, right? Because if we do it 12 times, a monthly rate becomes an annual rate. But if we're asked for an annual monthly rather than a monthly, then we would take that monthly rate and multiply by 12. And you end up with a smaller, right? So it was 5% rate, annual, but you get 4.9% annual monthly. That's because you're calculating more frequently the interest owed. And so to get to the same amount of money outstanding at the end of the life of the loan, you would need a smaller interest rate since it will be applied more times. We can do the same thing for continuous rates rather than monthly rates. It involves taking a logarithm instead, but works fairly similarly. Now, solving these problems using logs and roots is an option, but it's not the only option of solving these problems in class. So another option is to use a financial calculator Like a TIBA 2 Plus, these are sold for $20 in retailers nationwide. You can also use a website I've created that has some of the similar functions as a financial calculator. It's financialcalculator.com. And so what happens in financialcalculator.com is it allows you to put in inputs with the different kind of rates that you would expect to see. And then we can convert those rates using the simple tool. So let's just take a look at that here. So here's financial calculator. And we had that 5% rate. All right, so we had a 5% rate. Let's see how I've written that. So 0.05, 5% rate. And we want it to, it is right now, right? So right now, we have an annual rate. So why did I do 12-12? So this is 12 months, 12 months. And that's how you read this on this calculator. We pick a time frame, a time word really, months, and we do 12 months, 12 months. And we are interested in getting this rate as a 12-month, 1-month rate. And so this was an annual rate before, and that's you do it, old on top. We wanted to convert it to an annual monthly rate. And then we get that number, which we see in the slides, right? If we wanted, then you have to reset this like that. If we wanted this as a monthly rate, we could calculate that too, right? And we could also get it as a quarterly rate, reset it back to 5%. Calculate. So it facilitates doing interest rate conversions because you can do them pretty quickly relative to trying to solve them with algebra. So this is a resource available to you if you choose to use it. There is an interest rate conversion utility on a TIBA 2 Plus, but it is significantly more complicated than this one, and so it's not really our preference for this class. These buttons up here, PV, FV, IY, payment, and N, are identical to what you'd see on the TIBA 2 Plus, and are used the same way, or at least very similarly. And so this portion of the calculator would be very familiar to you if you were used to using a TIBA 2 Plus, but this takes on a little bit different format. Okay. So if I get 3% every quarter from my loan, how much will I earn every year? So that would be a pretty simple question in this situation, right? We take 3%. This is what we get every quarter. So quarters are 3 months each. And we want to know what that would be in 12 months. If you've done it right, you can read it as 3 months, 3 months, 12 months, 12 months. Right? It's tempting to do something like this, right? It's 3 months, 4 times a year, but that's not how it works. 4 times is never what you want to do. It has to be a time word. It's 3 months, 3 months. We calculate and get an annual rate, an effective annual yield for our quarterly rate that we had. So that's thinking about interest rates. It's important to do conversions, in particular because the formulas we'll use in this class require the interest rates of the units and the interest rates used in the formula to match the units in the problem that they're being applied to. So if you have a quarterly problem, you need a quarterly rate, and it may not be given to you, so you have to make a conversion. So then in the next part, we'll do some examples and take a look at applying interest rates in the time value of money.